how to do anything with these inductive definitions. All right.
Coming down.
So someone needs to mute themselves. Let's see. Otherwise, you're getting recorded here. All right. Hopefully, you know who you are. All right. Let's move forward. So now I've done these inductive definitions, but it's boring unless you can work with it. So let me pose a problem here. Let's go back to one of our favorite and very first inductive definitions. So let's go back to a simple problem. And for that, let's go back to numbers. Okay, so let's go back to the grammar of numbers. So we did this earlier. Natural numbers were either 0 or successor of natural numbers. This was the very first thing we did, and we translated this into Scala, right? So let me bring this over. And you have the seal trait natural number. You have the case object z, and z stands for 0 here. I'm a little tired of writing 0, so I just called it capital Z, extends natural number, or it's the successor of n, which is a natural number. So this is successor of a natural number. Okay, so now I want to have the following. So I want to define a function. Let's define the simplest function, right? I want to define the function subtract 1. So subtract 1 takes in a natural number, and I want to return a natural number, which is the natural number that's 1 less. And if it is 0, then I want to throw an error. So here I want to say return the previous natural number, raise a bug or error if n is 0. So ideally, a function like this, what do I want? So ideally, I want something like this. So ideally, if you call, for example, if you call subtract 1 on, let's say, successor of successor of successor of 0, what should be the result? What result do you expect if I call subtract 1 on successor of successor of successor of 0? So 3 successors. No, not throw an error, right? You would only throw an error if you want to subtract 1 from 0, because you don't have -1 in your language. So the rest of, yes, you're right. So you want successor of 0. So you want, this is equal to 2, that is 2. That's my, funky representation for 2, right? And here you have a funky representation of 3. Okay. So I want to do this, right? And of course, just because the student mentioned subtract 1 of 0, I want to raise an error. Okay, so what's the idea here? So I want a way by which, given this n, so what do I want to do? I want to say, given this n, see if n is of the form suck of something, and then return that inner something. Okay, so I want to do this, right? So given this n, I want to somehow see that is n of the form successor of something. If it is so, then I want to return that inner thing inside the successor. Otherwise, I want to say if n is of the form z, it's just a 0, then I want to return raise an error. Okay, how do I do something like this? There are 2 methods to do this. The first method is called the visitor pattern. Okay, and this is so important that it is worth talking about it. It's called the visitor pattern. And what's the idea here? The idea here is you do it from inside the class. So you are going to write a function, but the function is going to be written inside the class, not outside the class. How do you do that? Well, you're going to do it like this. So inside, now that you have this definition, inside each of these definitions, I'm going to write sub1, which is going to be my subtract 1 function, okay, and which is going to return a natural number. Inside my seal trait, I just declare this. I'm not going to define this because I cannot define it inside the seal trait. So I'm just going to declare it inside my seal trait. And then I am now going to, if I just did this, I'm going to throw an error, and you will see this in a second. So the error says object creation is impossible since method sub1 defined in trait natnum is not defined in Z. So what's it saying? It's saying that if you want Z to properly extend natnum, then you also want to define a version of sub1 inside Z. If you want to do this inside, so you better define a version inside, okay, inside suck as well. Is this okay? Now, here's the main advantage. Two advantages. One advantage, when I define sub1 inside Z, I know the context. I know the context because the context is I am trying to subtract 1 from 0. Okay, and so I'm going to say, I'm going to get all huffy and puffy, and I'm going to throw an exception. So I'm going to say throw. So let me cut and paste this because I've done this before. Let me cut and paste this and walk you through it in the interest of time. So I'm going to throw a new exception, and there are many built-in exception types in Scala, and one such type is called illegal argument exception. So I'm going to throw an illegal argument exception, which is, and inside that I give you a friendly message as to why it's illegal argument. It says -1 cannot be called on 0. Or I should say sub1 cannot be called on 0. Okay, and this is going to be the implementation for this. All right. Now, what about sub1 inside successor? Here comes the second advantage. Remember what I wanted to say is I want to see if n is of the form successor of something and return that inner something. Well, if I am in this method, then my class is of the form successor of something. Otherwise, I wouldn't be here. And what should I do? I should just return that inner something. Well, that inner something now has a name, and that's called n. So I'm just going to return n. Okay. So this is one way of doing it. And then my subtract 1 method is very simple. I'm simply going to call n dot sub1 and be done with it. Because n dot sub1 dispatches to this sub1 if n is a successor, otherwise it dispatches to this sub1 if n is not a successor. Okay, so question, why object versus class between sub1 and suck? Well, the object is here for Z, and the reason we did that was we didn't want to write Z open bracket, close bracket everywhere, right? So if you want to avoid that, you just write object. Okay, this sub1 is a method, so it's a function. So it's the name of a function. It's a member function. So this is a public member function, and it's a public member function that's defined inside natnum. So remember, a trait is an interface. It's a specification of an interface. So if Z must extend this trait, all right, then it must really do this. Okay, so question, is successor, okay, why is it just n and not n-1? Okay, here's the thing. When I am in this class, this entire class is successor of n. So it's n plus 1. So to subtract 1 from n plus 1, because the whole thing is successor of n. So if I want to subtract 1, I should return n. That okay? Because I'm working from inside the class. Here is where the confusion stems from, right? I'm actually working from inside the class, not from outside the class. Is that okay? So these are defined as proper members of the class, right? So in that sense, I should be careful. I should be careful in how I interpret things. So this is the inner thing. Okay, could you represent 0 as successor of 0 dot sub 1? Very good. Let's talk about it. So is this okay? Does this sit well with everyone? So now let's see, can do val 1 equals successor of 0 All right. And then I can say subtract 1 of 1, and that gives me 0. Okay. So question, does it check Z first or successor first? Okay. Here's the cool thing, right? When I call subtract 1, it just takes this object n and calls n dot member function sub1. All right. Now it depends on what n is. So here is where the if then else happens, but it happens because of the way that classes are built, right? So the way classes are built, n dot sub1 either dispatches to this z dot sub1 or this suck dot sub1. It depends. If n is a z object, then it dispatches to this. If n is a successor of something object, it dispatches to this. And that's where the checking is happening, but it's implicit in the way Scala has done the classes. In a second, I will talk to you about how to do it explicitly, right? All right. Is this okay? This is very sneaky, right? I'm sneaking in. Yes, exactly, right? So this is a form of polymorphism. So essentially, it's a form of dynamic dispatch. If you have seen in C++, it chooses Z or suck based on the type of the runtime type of n. The runtime type of n is either a Z object or it's a suck object. Okay, so far? All right. How do I write it in a different way? And in the different way, I'm going to come across a very, very powerful feature of Scala called case pattern matching. So in case pattern matching, I'm going to write this function from outside. I'm not going to bother extending the definition from inside. I'm going to write this function from outside. And how do I do that? Well, this is going to be very much like the case statement or the switch statement in C++, except it's on steroids. It's going to be so much more powerful. So what is it? So you are going to write it like this. So you're going to say n match. So this is this n, the argument of subtract 1. And I'm going to say match. And then I'm going to say case z. If n happens to be of a z, then raise this illegal argument exception. Okay, so this is writing the whole thing from outside. Okay, so you can say subtract 1, or it's the case that it's a successor of some inner thing. In that case, return the inner thing. So this is using something called case pattern matching. So when I call, for example, subtract 1 of 1, so this n becomes suck of z. So this n here is the same as suck of z. And now I am matching on this n. So when I match on this n, I match is the suck of z match z. And obviously suck of z does not match z because the outer term here is starting with a successor and here it's starting with z. So you cannot match them. Does suck of z match suck of inner? Yes, it does. Suck matches suck. And now inner is a val. So inner is a val that automatically in runtime gets the value of whatever is inside. And in this case, whatever is inside is going to be a z. So inner just becomes a z. So when I call subtract 1 of 1, hold on. Subtract 1 of 1, I automatically get return the z. So this is a way of doing it from outside using this powerful feature called case pattern matching. Good so far? All right, so let's go ahead and try and explore this case pattern matching because we are going to use it a lot in this class, right? So why not explore it more? So now I would like to write a function, define add, which is going to add two natural numbers, n1 and n2. Okay, so I want to add two natural numbers, n1 and n2. Okay, so the idea here is going to be like this. So I'm going to write it as a recursive function. So I'm going to write it as a recursive function. And the idea here is this. If n1 is 0, So if n1 is the same as 0, then what should the result of adding n1 and n2 be? No, n2. Okay, good. Maybe you got the index wrong. Yes, n2, right? So if it is 0, this is the base case. So this is the base case. Otherwise, else, I'm going to say in this case, okay, this is just pseudocode. This is just pseudocode. So bear with me for a second while I'm commenting out the pseudocode. Otherwise, it tries to think of it as Scala code. Else, I'm going to say n1 must be successor of something else. So let's call this n1 hat. So then I'm going to say, and this is where the sneaky part comes in, I'm going to say the result is the same as adding the inner thing n1 hat to successor of n2. So remember, n1 is some n1 hat plus 1. And that plus 1 that's currently at n1 hat is transferred to n2. That's going to be the strategy. All right, that's going to be the strategy for addition. So this is implemented using case pattern matching. So I'm going to say n1 match. If n1 is a z, then simply return n2. If n1 is a successor of some n1 hat, then recursively call add on n1 hat and move the successor or the plus 1 over to n2. This is my addition function. Oh, this is just the name of a variable. So the idea here is, when I pattern match on n1, the outermost constructor on n1 is a successor. Then everything that's inside is going to match to n1 hat. So n1 hat is a val. So n1 hat is a val that gets created. It's, basically, technically in mathematical terms, it's going to be n1 minus 1. So n1 hat is going to be n1 minus 1 because it's the inner thing in n1. Oh, does the term hat have any significance? No. So I could have called this n1 inner, right? It's just my name, right? It's just my name. I could have called this name. It's just some name that I have to give to the thing that's inside. Okay, and that's the reason I have it set up this way. Or I could have called it K. Doesn't matter really, right? But n1 hat, because I put n1 hat here, I'm just going to use n1 hat. Okay. Recursive method result needs a result type. So the point is, whenever you have recursion in Scala, you should never forget to write the result type of the function, or else Scala is going to be mad. Oh, very good. So some student really got the idea. Are we taking the successor out of n1 and giving it to n2? Exactly. That's all we are doing. And now you can tell me why the loop will terminate, or why this recursion will terminate, right? Exactly. And we are eventually reaching when n1 is 0. Very good. Very good. Uh, Glad you got it, right? But you can see how this case pattern matching is so powerful. And the power of case pattern matching really comes not because it's able to differentiate between Z and suck. It's also able to give a name for what's inside. So you can actually write something inside, and you can put it around curly braces or not, depending on whether what you're going to write is big, sequence of code, or just one single expression. So as an example, let me define val3 equals successor of successor of successor of 0, and then val4 equals successor of 3. So that defines two numbers. Then I can define val7 equals add 3, 4. So now you have this whole thing. And the nice thing is it's tail recursive. So you can write your annotation, add tail rec, and Scala will come in and turn it into a tail recursive function. Very good. But why are we doing this? Isn't addition a bitwise operation that runs in O1 time? And doesn't this turn it into a log O n operation? Okay, uh, let me correct a couple of things. Addition is not a O1 operation on a computer. Addition of a number n would be O log n. Okay, it's the number of bits of n, so O log n. All right. Okay, out of the way. Yes, this is no way to do addition. This is just an exercise in case pattern matching on a very simple operation. All right. And this kind of representation of numbers is a unary representation of numbers. It's a very inefficient representation of numbers, right? You're doing unary representation. You're not even doing binary representation. So this is bad. I mean, I'm not saying this is how you should do things. All I'm saying is, here is a nice example of how to do things, right? I'm not really going to recommend this as anything you should be doing. Okay. I hope that's okay. So how do you do it from inside? Well, you can do it from inside too. So you can say add number. And here, remember, when you're defining it inside a natnum, one of the arguments is already given to you, because you're always going to call this from inside. You're going to call it as something like this: n1.addNum n2. So the n1 is the this argument, and then you would use addNum, and n2 is the argument that would be inside. So I just need one argument here, n2, because n1 is already given to me, right? Because n1 is the this argument. The class in which I'm writing this is implicitly an argument. And then if I'm inside the 0 class, then if I try to add a number n2 to 0, then the result is just n2. If I am inside the successor class, and if I try to add a number n2 to a successor class, I just say this is the same as n, the inner thing here, n dot addNum successor of n2. So this is how I would write it inside the class. And using case pattern matching, this is how I would write it outside the class. Right? Here I would say 3 add 3 4. Otherwise, if I wanted to do it from inside the class, I would say 3 dot add 4. What was it? Add num 4. Add num 4. Okay. I hope this is fine. All right. So I'm almost to the end of this class. So we started looking at case pattern matching, which is going to be a very powerful feature in Scala. So next lecture, I'm going to start with case pattern matching. I'm going to show you some very seriously, complicated things you can do with case pattern matching that you couldn't do without case pattern matching. That becomes very, very difficult to do otherwise, which makes case pattern matching very, very powerful. Now I'll tell you one last thing before I conclude this class. I can now truly tell you, why did we call these case classes? And the reason we call these case classes is because you can use these classes as patterns in case pattern matching. So the reason we call it case classes as opposed to regular classes is that Scala allows you to then do matches using case pattern matching. And that's why when you do this kind of a thing, when you say case suck inner, it better be a case class. Suck better be a case class. If it's not a case class, you will never be able to pull this off. All right. So with that, I will stop today's class, and I will see you next lecture, where we will talk more about this thing. So we are not done, even like scratch the surface of case pattern matching. So we're going to say more about case pattern matching, and we are going to say that next lecture. All right. Thank you so much, and I'll see you next lecture.